All right. So yesterday I started talking about what we call as a conservative force. I'll continue explaining this concept. The motivation is to eventually go back to the work energy theorem. If some of the forces acting on the rigid body of interest happen to be conservative forces, then we can show that the work energy theorem simplifies further. The algebra of the work energy theorem simplifies. Indeed, that is the only motivation we are worried about, whether a force is conservative or not. Yesterday I was saying that a conservative force is such that the work done by that force does not depend on the path taken by the particle on which the force is acting. If you pay attention to this side of the screen, I was trying to show that there exists a conservative force F in the background and a particle is following this path. At time t1 it was here, at time t2 it is here. If I want to find the work done, the net work done by this conservative force on this particle during this time t1 and t2, it will turn out that the work done will be independent of the path taken by the particle of interest. The work done will depend only on the initial position and the final position of the particle. That is the characterizing feature of a conservative force. Strictly speaking, I should talk about a conservative force field, because that conveys the idea of conservative force in a better manner. Force field. When I say a force field, what I am trying to say that there exists a force in the background, and that force, its magnitude, its direction varies very continuously with location in space. So if this screen is our space, if you go to this point which has coordinates primes 1, 2 and 3, this conservative force field is such that at this point there is a force acting with a magnitude and direction as specified here. But if you go to another location in space, the same force field rather, will change its magnitude and direction to something else, shown here by this arrow. Gravitational field is an example of a conservative force field. Gravitational force field exists everywhere. If you are the particle or you are the system of interest, you go anywhere, the force kind of follows you. Its magnitude, its direction may vary with where you are right now. If you are very close to the Earth's surface, yes, you can say that the gravitational force field is constant. You go anywhere, it's the same, m times g, where g is always pointing downwards. But if you go like 5,000 kilometers away from the Earth's surface, you are talking about interplanetary probes, spacecrafts, then the gravitational force will start also changing with location, right? So such is the idea behind this conservative force field. In general, I would like to write the conservative force field as this. It has three scalar components referred to a coordinate system of interest that I have fit here in reference frame F. It will have a component along E1, a component along E2 and E3. And I have put these x1, x2, x3 in the parenthesis here, indicating that these scalar components are actually functions of where the particle of interest is, the location. Conservative force has no dependence on time. Again, it will be more accurate to say that the conservative force field has no dependence on time. There is no time appearing anywhere. So today or tomorrow you go to the same location, you get the same magnitude, same direction of the force. Yeah, at a given time instant it changes with location, but you fix yourself to a location today, tomorrow, day after, it still remains the same. Okay. Now I say the force field does not have any dependence on time, but then visualize if a particle itself is moving in space, that particle will be at different location at different time instants, right? So if you start following a particle, that particle will be moving in space, changing its location, and thus the force that it experiences because of this field will definitely change. But only when you follow a particle of interest. If you don't follow any particle, if you just look at the force field, no dependence on time. I would like to go back to this diagram which I showed yesterday and today also. So I am saying the particle is following this path. As the particle follows this path, it changes its location, and depending on the location, the force arising because of the conservative force field will be different as experienced by the particle. But you focus your attention only at this location at all times, the force vector will remain the same magnitude, same direction. Okay. I also talked about an associated potential function with a conservative force field. A conservative force field has an associated potential function, and we represent that potential function, which is a scalar function, by this symbol V, and then I put in the argument x1, x2, x3. The potential function also changes with space, but not with time. You come tomorrow, day after, you will still see the same value of the potential function at a given location. Now this potential function is actually defined in a way such that the difference between the potential functions at two locations. So say this is the first location and this is the second location. The difference between potential function at 2 and the potential function at 1, you take the difference and you put a minus sign in front of it, or it is the negative of the change in potential. That happens to be the net work done by this force on a particle which has moved from location 1 to 2. This is the work done as the particle goes from location 1 to 2. Work done has to be F dot dr, and that can be represented as difference in the potential function of that conservative force. Yesterday I showed that the three components, scalar components of this conservative force field are actually related to the potential function derivatives in the manner written here. Minus of partial derivative of b with respect to x1 is f1, and similarly you take partial derivatives with respect to other coordinates and you will get the second and third components of the force vector. I want to remind you again about the definition of partial derivatives. I am sure it has been taught in one of your maths courses. Sometimes I teach a second year course in fluid mechanics, and I have found that many students in the second year, they don't know what these symbols actually mean. And that is why while teaching this course, I feel it is my duty to remind the students that you have been taught these definitions, and do keep these in mind. Okay, partial derivative with respect to x1 will be this difference in the value of b at two locations divided by delta x1 going to 0. But the two locations are chosen very carefully. x2, x3 do not change. x1 and the first coordinate is changed by a small amount delta x1 independently. Okay, such is the definition of partial derivative. So this is the relationship here. Now if I give you a force field, suppose I give you a force field AX1, AX1 E1, BX2 E2, CX3 E3. This is a force field. I can tell you A, B, C are constants. How do we judge whether a given force field is conservative or not? I am going to explain how we judge. It involves a little bit of derivation and again little bit of knowledge borrowed from one of your maths courses. My understanding is that in one of your first year maths courses you have been told what Stokes theorem is about. Stokes theorem. Proof must have been given. I am not going to give proof. Proof not in this course. I am just going to use Stokes theorem. That's what I meant, that I would borrow something from one of your maths courses. I would like to remind you what this theorem is about. In Stokes theorem, this f that is appearing on the left hand side is any vector function which depends on space, like our conservative force field or like any force field. Okay, this is a vector function. Okay, I call it a vector function because it has three components and those components do depend on space. What is dr? Rather, what is this whole integral f dot dr? So the force field exists on the screen, on this blackboard. You take a curve, closed curve C, and then you start integrating f dot dr. What is dr? Dr is this. This is a small segment of the curve, and we are associating a vector with that. Not hard to visualize. This segment has a magnitude and it will have some direction after all. Say I have a coordinate system fix here. dr can be written like dx1 okay, and f is like this. So you take this f dot dr and integrate it along this closed curve, along this closed curve. Take this along this closed curve. That this can be called as a line integral. Left hand side is a line integral. Okay. Stokes theorem proves that this is going to be equal to an area integral. Okay, this is area. Which area? Area enclosed within the closed curve, within the curve C, this area. Now what is inside this integral? Del cross F. What is del? This is called the del operator. In Cartesian coordinate system, it is written as it's an operator. It acts on other things. This is being taken as this is crossing. There is a cross product with F itself. So how do you get del cross F? You can use this kind of can get this cross product in this manner. Right? I'm sure you know how to get the full expression out of it. So it is del f3 del x2 minus del f2 del x3. That's the component along E1. Along E2 you get along E3 we get okay. That's what goes in here. And what is a dA? dA is a vector. The magnitude of this vector will be the area, a small area that I will take here on this full area, infinitesimal area, dA. Infinitesimal area. So dA is this magnitude, which is infinitesimal area, and En. What is En? Outward normal, unit vector. Now outward normal can be coming out of the screen or going into the screen. The direction of En is decided how you are taking DRS, which direction you are taking dr as positive. If this is the way I am taking dr to be positive, En will be going inside, En will be directed into the board. It will go inside the board. This is how it is oriented. Line integral to area integral. Now let's recall that if f is conservative, it means f dot dr from location 1 to 2, what did we say? It's going to depend on difference of this potential function. Right? But if I take this integral from 1 to 1 along the loop, after all this is a line integral, along a closed loop if I take, what am I going to get on the right hand side? I am going to get 0. Initial and final location are the same. Which means that Stokes theorem, if I invoke, according to Stokes theorem, if you go and try to take line integral of a vector function along a closed loop, you should get what? You should get this area integral. There is a dot product here. We did not highlight it. But left hand side is 0 for a conservative force. It means this should be 0. Okay. Now this closed loop can be taken. I can shrink this closed loop. I mean, on every closed loop with f as a conservative force, if the vector function f is a conservative force, on every closed loop you are going to get this. On every area, I mean, on every area you are going to get this 0. How to judge whether a given force field is conservative or not? You start with a given force field, First check whether it changes with time or not. If it does change with time, today and tomorrow it will change, then that force is not conservative. Right away the conclusion comes. If it does not change with time, no. N means no. This means yes. Then you have to do another check. Is f constant in space? It does not depend on time, does not depend on space also. It's a constant force. F is conservative. You can conclude right away. But suppose it is not constant in space, then you go and do this test. Is del cross f 0? If the answer is no, then f is not conservative. If the answer is yes, f is conservative. Now if you think about it, even this thing, the f constant thing, if you want, you can remove this box and directly go here. That will also give you the right answer. Still I have put this box here because if it is a constant, then you really don't have to do this, take this cross product. You can right away conclude and you will get the right conclusion. So overall, this is the way we judge whether the force is conservative or not. Let's have a look at an example. Given a force field, a force field is given. X0 is constant, K is constant. I have some coordinate system. Okay. Two questions. Is the force field conservative or not? And if it is, find its potential function. Find the potential function of F. To judge whether it is conservative or not, I will use this table, this flow chart. Does the force field depend on time? First question, first decision box. No, it is not depending on time. Second decision box, is it a constant? Is it a constant? No, it is not a constant. It is depending on x1. Third question, I come here. Is del cross F 0? I'll have to check. Let's check if del cross F is 0 or not. Okay, this force has a component only along x1. Non-zero component is only along x1. The other two components are 0. You can check, this will turn out to be 0. Almost visual. I am not writing all the steps, but this will turn out to be 0. Flowchart. Does not depend on time. No. Does it depend on time? No. Came here. Is it a constant? No. Is del cross F 0? Yes. Conclusion is force is conservative. Force field is conservative. Now if it is conservative, I need to find its potential function. How do I find its potential function? Yesterday I derived this three equations. We will use all three of them to find V. If F1 is minus del V del X1, I am going to integrate this equation first. So F1 I know is minus K X1 minus X0, that is minus del V del X1. Let's integrate this with respect to X1. dx1 dx1 integrated. I get if you integrate both sides with respect to x1, this is the conclusion I will get. This function will integrate to k x1 minus x0's whole square by 2. The right hand side will integrate to simply v. After all, we have only v here, del v del x1. So you get right hand side as v. But then I am not sure about this part, what it will be, but at least I know this much, that there has to be a function, there may be a function of x2, x3 or a constant that needs to be added to the left hand side to equate it to v, the potential function. Alright, now let's go and integrate this. F2 is 0. I am going to integrate both sides with respect to x2. Function of x1, x3 or a constant, and on the right hand side you will have minus v x1, x2, x3. So every integration is giving me v x1, v at x1, x2, x3 on the right hand side, but left hand side I am getting different types of information, and I keep gathering all that information. Let's come to this. F3 is 0. Integrate this time with respect to x3. You get 0. 0 plus a function of x1 or x2 or a constant equals minus v times x1, x2, x3. Three types of information about v, and all of them are true. All of them are true. So to get to final v, I have to look at all three and then decide what the form of v should be such that all three conditions are satisfied simultaneously. Okay. Now if you pay attention to all the conditions, you should be able to get to the conclusion that v should be V should turn out to be kx1 minus x0 whole square by 2, which I got from this, plus a constant. This is the only resolution from 1, 2 and 3. Okay, so this is the function V. Conventionally, we never bother about a constant, and thus my conclusion would be constant is ignored, and thus V in this case is there is a good reason why this constant is ignored. Mind you, the way I am going to use the potential function is to find the work done by this conservative force field on a particle which moves from 1 to 2, and we know that it turns out to be the difference in the value of V at two locations. Difference, always, difference is important, difference matters. Since only the difference matters, you include a constant or you don't include a constant, it will not matter. F dot dr is not affected. Thus, conventionally, we don't worry about that constant. So this is the answer to that question. You are familiar with this force field, very familiar with this force field. This is the force field of a spring which has its unextended length as x0, and then if you extend it more, it starts developing a force. Spring force field. And this V that I have arrived at, this is the potential function of a spring force field. We also associate this quantity with how much energy is stored in the spring, potential energy of the spring. Different ways of referring to the same quantity. The bottom line is this is the scalar function or the scalar potential function associated with that spring force field. Let's take one more example, and this example is very close, very familiar. Example: conservative force field is constant. All are constants. Different constants, may be different, but constant nonetheless. So constant force field. Does it depend on time? Of course not. Is del cross F 0? Yes. A constant force field is always conservative. What is its V? Let's find its V. Integrate with respect to x1. I get f1 x1 some function of x2 x3 or a constant. Right hand side I get V. Another function of x1 x3 or a constant another function, possible function of x1 or x2 or a constant. Again, compare, look at all of them simultaneously in perspective and come to a resolution. The resolution is what is the resolution here? Here the resolution should be V is this is the resolution. Again, give or take a constant, it doesn't matter. Nobody bothers about a constant. Put a constant, don't put a constant, doesn't matter. This is the potential function. Special case. Gravitational force acting downwards, coordinate system oriented in this manner. The force is m times g minus e2 direction. That's the force field. It is a constant. Okay, so F1 is 0, F2 is minus mg, and F3 is 0. What should be the potential function? Potential function should be minus F2 x2. is minus plus mg x2. A result that we have used for a long time. We call it potential energy of the body. Again, call whatever you want. This is the potential function of the constant gravitational field in which the force vector acts along minus E2 direction. Gravitational potential. Okay. Let's come to the primary question of interest. How does the realization that a force field is conservative help us simplify the expression for Pi? Recall, Pi is the rate at which the external force system is doing work on the RB, this RB, with respect to frame I. How does it affect? How does it simplify? I'll talk about it. Let's take a break. Let's meet at 2 past 5. 2 past 5.